existence of correlations between events at a distance should not surprise a scientist. The goal of science is to find a rational explanation of correlations. For instance, if I push on a button here and a light turns on there, I have a causal explanation of the correlation between the two events, invoking an electric circuit that I close and current flowing in the bulb. Pushing on the button is the cause of the light shining. Two events can be correlated, even if one is not the cause of the other one. For instance, two persons in the same room will see the light shining at the same moment. The perfect correlation between these observations is due to a common cause. Somebody pushed on the button and the light was switched on. Can we invoke such a standard scientific explanation to understand the correlations between polarization measurements on EPR correlated photons? At this point, you may ask the question, what is the meaning of understanding for a physicist? The answer depends on individuals. Many quantum physicists, following Niels Bohr, would probably answer that a mathematical formalism predicted the observed correlations is enough as an explanation. This is the shut up and calculate point of view. But other physicists like to think of explicit mechanisms which can be represented by image as a complementary explanation. Bill Phillips, a well-known expert on ultra-cold atoms, once said, "During the week, I belong to the shut up and calculate church, but on Sundays, I visit other churches." In fact, even if they pretend to belong to the shut up and calculate school, many physicists use images inspired by the calculation. Think, for instance, of a polarized classical electromagnetic field. Most of us think of arrows in space to represent the vectors obeying Maxwell equations. Can we, similarly, build a representation of polarized entangled photons associated with the quantum calculations developed in the previous section? Remember the calculation leading to the probabilities of a joint detection. It consists of projecting the state vector psi of nu1, nu2 onto the eigenvector plus A plus B associated with the result of the joint measurement we are interested in. Can we represent that mathematical operation in our space? I doubt it. At least I cannot, since these vectors belong to an abstract Hilbert space, which is a tensor product of the space describing the first photon polarization by the space describing the second photon polarization. A space which does not correspond to ours. So, should we renounce building images in the space where we live? It is interesting at this point to recall a strong statement of the late Asher Perez, a well-known theorist of quantum physics. He said, "Quantum phenomena do not occur in a Hilbert space, they occur in a laboratory." I have spent many hours in a laboratory, and I can tell you that it is a place that belongs to our ordinary space. So we should look for an image in this ordinary space where we live. In fact, it is possible to derive an image in our space based on a detailed quantum calculation. For that, let us assume that the measurement at polarizer 1 happens first, and then the other measurement is done at polarizer 2. Quantum calculations tell us that at polarizer 1 we can obtain either +1 or -1 with equal probabilities, whatever the orientation A of the polarizer. To be specific, take this polarizer along X. What happens then after that measurement at polarizer 1? You can find the answer in any good textbook on quantum mechanics, such as the one of Cohen-Tanuji and company. You must use the so-called projection postulate, which tells you that when a measurement is done, the initial state vector is projected onto the eigenspace associated with the result of the measurement. Let us apply the recipe to our case. Remember that polarizer 1 is aligned along the x-axis just after the measurement, yielding +1 for nu1, that is to say associated with the x polarization for photon nu1, the initial state vector must be projected on the subspace associated with x1. After normalization, the result is the state vector x1, x2. If you do not know how to do that calculation, you will find details in the quiz at the end of this section. The state x1, x2 is factorable and describes the pairs of photons, each with a well-defined polarization. Photon nu1 is polarized along x, which is not a surprise, and photon nu2 is also polarized along x. If a measurement is done on nu2 with polarized 2 along x, one will find +1. Similarly, if one had found -1 for nu1, that is to say a y polarization, the projection would lead to y1, y2, that is to say a photon nu2 polarized along y. A measurement on nu2 with polarizer 2 along x would then yield -1. We recover the total correlation found by the global calculation for the case of parallel polarizers. If now polarizer 2 is at a different angle, a straightforward generalization leads to the cosine squared variation found with the global calculation. We have thus found an image in our ordinary space. Should we be satisfied with that image? Einstein was certainly not happy with the description in which the measurement on photon nu1 instantaneously affects the state of photon nu2, which is at a distance. You remember, of course, that Einstein was the discoverer of the relativity theory, in which nothing can travel faster than light, so nothing can be instantaneous. An image such as the one just presented, derived from the standard quantum mechanics formalism, was unacceptable for him. That led him to question the completeness of that formalism. Indeed, one would have a more reasonable image if one would accept to complete the formalism of quantum mechanics with supplementary parameters. Let us suppose, indeed, that the two photons of a pair share, from the moment of emission, a common property, lambda, that will determine the outcomes of the measurements on each photon. The result of the measurement at polarizer 1 would then be given by a dichotomic function, capital A of lambda A, with values either +1 or -1. Similarly, a function capital B of lambda B would give the result of the measurement at polarizer 2. Correlations would then be as easy to understand as the similarities of identical twins who have the same eye colors, sex, diseases, etc. The supplementary properties looking like lambda are obviously the identical chromosomes of the two twins. Coming back to our photons, we can render an account of the randomness of each individual result by introducing a random distribution rho of lambda of the parameters lambda among the successive pairs. These distributions have the standard properties of a probability distribution, positive and normalized. Some models of this kind can reproduce some strong correlation predicted by quantum calculations for the EPR state. Consider, for instance, a very natural model, the one many of you would invent, I am sure, after some thinking. Assume that when the two photons are emitted, they have a well-defined linear polarization characterized by their angle lambda with a vertical axis. The result of a measurement at polarizer 1, oriented along A, will be given by a dichotomic function capital A of lambda A, taking the value +1 if the polarization of the photon is at less than pi/4 of the polarizer axis, and -1 if the polarizer is at more than pi/4. Check that the function written here does the job. A similar function is written for polarizer 2. The distribution ρ of lambda is taken uniform. A simple calculation, which you can find in a document attached to this week lesson, then allows one to calculate the expected probabilities of simple and joint detections. The single detections are found totally random, as predicted by the quantum calculation. The joint probabilities lead to a correlation coefficient plotted here. You see that for angle 0, or pi/2, the simple model yields a full correlation, as the quantum prediction. More generally, the quantum predictions are not very different from the ones of the simple model. Such a model to understand the EPR correlations is appealing and as rational as invoking chromosomes to understand similarities in identical twins. But this model amounts to completing quantum mechanics since one considers different kinds of pairs with different values of lambda, while in the quantum formalism all pairs are described by the same state psi. It turns out that Niels Bohr, who had made immense efforts to develop a consistent interpretation of the formalism of quantum mechanics, was deeply convinced that it was impossible to complete that formalism, and immediately objected the conclusion of the EPR paper. His arguments, however, were not clear enough to convince Einstein. It is fair to say that the debate between the two old physicists did not attract much attention from active physicists who were using successfully quantum mechanics to interpret their discoveries. In fact, you must realize that it was a debate about interpretation only, not about the mathematical formalism, since Einstein fully accepted the results of the quantum calculations. But he thought that these results should be interpreted, invoking properties belonging to each photon, in order to avoid the apparent instantaneous influence at a distance at the moment of the measurement. The debate between the two giants lasted until Einstein's death in 1955. 10 years later, the discussion would take a new turn with a far-reaching discovery by John Bell. Einstein's point of view would lead, in some very rare circumstances, to a conflict with quantum predictions.